What is up, young chemists? Mr. Rosen here. Today we're going to talk about stoichiometry. We're going to do some mass to mass and mole to mole stoichiometry. This is a very important concept in chemistry. It's used really throughout the year, especially the whole second semester. So stoichiometry is really all about during a chemical reaction, you have reactants getting used up and you have products being formed. And the way that those two change over time, it's kind of what stoichiometry is all about. Stoichiometry is really chemical calculations with chemical equations. As the reactants are used up, how much product is formed. And it's really answering the kind of question where, you know, if you have a chemical equation, like let's say we have this equation on the page, and you start with a certain amount of nitrogen, how much NH3 could be produced, right? You should be able to calculate that ahead of time, and then you can actually do the reaction and see how efficient your reaction is. So, as it says, stoichiometry involves the changing amounts of reactants and products during a chemical reaction. The balanced equation is really important. You have to have a balanced equation, and we use the coefficients in the balanced equation to find out information about the relative ratio of reactants to products during a chemical reaction. So we're going to start with mole-to-mole stoichiometry. This is the easiest variety or easiest style of stoichiometry problem. So it says, based on the balanced equation below, if you begin with 7 moles of nitrogen gas, how many moles of ammonia could you produce? So this is a typical stoichiometry problem. Now, it's already giving you moles, and it's asking for moles, right? This is, why we call this mole-to-mole stoichiometry, because you're going from moles of something to moles of something else. In this case, we're going from moles of this reactant, nitrogen, to moles of this product. Okay. Now, just like on a purely logical level, you should see that what this says is 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of NH3, which is called ammonia. Now, that also tells you that for every 1 mole of nitrogen that you start with, you end up with 2 moles of ammonia. So you could probably start to think about the answer to this question, really before you even set it up as a calculation. But we're going to go through the process because it gets more complicated in the future. So it says start by setting up this problem as you would any other conversion. Okay, so if we're converting, let's say, like a unit, if we were converting, centimeters to millimeters, we would start by writing what's given, okay, the thing that we have. So we have 7.0 moles of N2. And then we convert it by multiplying by some conversion factor, this is going to be something over something else. The unit that we're trying to find, sorry for the bell, the unit that we're trying to find goes on top, and the unit that we're given goes on bottom. So we have moles of N2, so mole of N2 goes on bottom, and what we're trying to find, the question is asking us about ammonia. So what we're trying to find is NH3, so that one goes on top. So we're trying to convert from moles of N2 to moles of NH3. Now, in terms of what numbers go here, the numbers are going to be the coefficients from the balanced equation. So the coefficient in front of ammonia right here, the coefficient in front of ammonia, NH3, is 2. So in front of NH3, we put a 2. And nitrogen is here. There's no number in front of nitrogen. That means that there's 1 mole of it, right? Because if it was 0, then it wouldn't be there at all and it wouldn't exist in this equation. But the fact that it's there means we have 1 of it. So it's 2 over 1. This is what's called our mole ratio. 2 moles of NH3 for every 1 mole of nitrogen. And you can see what's going to happen here. We're going to take 7 times 2, right? And moles of N2 will cancel out. and you'll be left with 14 moles of NH3. And that's really step 2 here. It says place the coefficient of what you're trying to find on top and the coefficient of what you're given and what you want to cancel on bottom. All right, this is what's called your mole ratio. You perform that calculation and you arrive at your answer. Right, so the balanced equation says for every 1 mole of this, you end up with 2 moles of this. So you end up with twice as many moles as you started with. So if we start with 7, we end up with 14. Right? If we started with 5 moles of this, we'd end up with 10, because that's 2 times 5. Right? Our mole ratio is 2 over 1. So this is a basic mole-to-mole stoichiometry problem. You're always given moles of something, and you're solving for moles of something else. So you cancel your unit by putting what you want to find on top and what's given on bottom. Now, we're going to do a couple of example problems here. Example problem number 2. It says, use the same balanced equation given in the previous problem. Maybe just for the sake of not having to flip back and forth, I'm going to write it here. We have N2 plus 3H2 gives you 2NH3. So that was our balanced equation. So we're going to use that same equation. Calculate the number of moles of hydrogen gas that were present before the reaction if 6.24 moles of ammonia were produced. Now this is a little different. Okay, in this case, they actually tell us how much product we end up with. And they're asking how much reactant we started with. So it doesn't really matter in terms of the math, right? The math that we're going to do is we start by writing what's given, right? What's given is 6.24 moles of NH3. In this equation, in this problem, that's what's given. Now again, we're going to be converting it to something else, right? So we're going to multiply it by our conversion factor. What we're trying to find in this problem is moles of hydrogen gas. So H2 is what we're trying to find, so that goes on top. All right, mole of H2, and mole of what's given goes on bottom. Now again, in terms of figuring out the numbers that go on top or bottom, the numbers are the coefficients from the balanced equation. So if we look up here at the balanced equation, see what's in front of H2. In front of H2 we have a 3. So in front of H2 we put 3. And in front of NH3 we put 2. That's our mole ratio, a 3 to 2. You need 3 hydrogens for every 2 ammonias produced. So if we take this number times 3 divided by 2, moles of NH3 will cancel out, and we'll be left with our answer in moles of H2. That would be moles of H2 needed. Okay, so on our calculator here, 6.24 times 3 divided by 2, 9.36 moles of H2. Right, and the equation's saying for every 3 of these, you end up with 2 of these, right? You end up with 2/3 of what you started with. So if this is how much hydrogen we have, that's how much we'd end up with. Or if that's what we end up with, then this is how much we had to have started with. Okay, this is a mole-to-mole stoichiometry problem. So we'll do one more. And then we're going to get into mass to mass, which is really the same middle step, but then some new calculations added on as well. So example 3 says, how many moles of oxygen gas are necessary to completely react with 4 moles of propane? So we have a new equation. The first thing we need to do is make sure it's balanced. It already has coefficients in it. And looking at this, I can see 3 carbons and 3 carbons. I can also see 8 hydrogens, 8 hydrogens. So this is a balanced equation already. Sorry about the bell. We're going to wait for a second. Okay. So this is already balanced, but we do have, again, moles of something is given, and moles is what we're solving for. So we start by writing what's given, 4 moles of C3H8 times something over something else. What we're trying to find is moles of oxygen. So what we're trying to find always goes on top, and what we're given goes on bottom. Okay, and these are both moles. Now, the numbers we're going to use are the coefficients from the balanced equation. In front of O2, we have 5. In front of C3H8, there's nothing there, but again, that's not a 0, that's a 1. A coefficient of 1 is not written, but the fact that it's there means there's one of them. Okay, so 5 over 1. And looking at the equation, it says for every one of these, you need 5 of these. So if we had 1 C3H8, we would need 5 oxygens. If we had 2 C3H8, we would need 10 oxygens. If we had 3 C3H8, we would need 15 oxygens. And in this case, if we had 4 C3H8, we would need 4 times 5. This cancels, and you're left with 20 moles of O2 is what's needed, right? Because for every 1 mole of C3H8, you need 5 moles of oxygen. We have 4 moles of C3H8, so 4 times 5 is 20. Hopefully the logic behind the mole-to-mole stoichiometry is starting to sink in a little bit. Now, these are nice, easy problems, but the reality is, most of the time, if a chemist or somebody, a scientist, is doing lab work and they have to do a stoichiometry problem, they're not working in moles, they're working in grams, they're working with masses. So we're going to do some mass-to-mass stoichiometry problems, which means starting in grams and going to grams, okay? So in our last problem, we went from moles to moles, and now we're going to start in grams of something and end up in grams of something else. Now, the middle step is actually the exact same as a mole-to-mole problem, but we have to do one conversion before, and we have to do one conversion afterwards, right? So we're going from grams to grams. It's based, again, on the balanced equation. So let's look at the example problem and see how it's different than the ones we already looked at. So this example problem says, based on the following equation, how many grams of LiOH, that's lithium hydroxide, are needed to react with 125 grams of carbon dioxide? So you see how this is different? They're asking about how many grams are needed when you start with grams of something. So you're given grams in this case, and you're solving for grams. When we were doing mole-to-mole stoichiometry, they give you moles of something, and you went to moles of something else. Now, the equation, which here, this equation is not balanced. I can see there's only one Li on the left. There are 2 Li's on the right. So this is an unbalanced equation. So the first thing we need to do is balance the equation. Okay? Once we have the equation balanced, the coefficients tell you the ratio of moles of reactants to moles of products, right? The balanced equation shows you the mole ratios. So we're actually going to have to convert from grams into moles. Then we use the balanced chemical equation, just like we did before, doing a mole-to-mole stoichiometry problem. And at the end, we'll take moles and convert it back to grams. So it's really, the middle part is a mole-to-mole problem. We just have to convert from grams to moles, and then at the end, convert from moles back to grams. All right? So let's go through these steps. It seems like kind of a lot at first, but with practice, you get the hang of it, and you'll see that it's actually not so bad. So the first step, balance the equation. Okay, I can see that there are 2 Li's on the left side, and there's only, there's 1 Li on the left side, and there's 2 on the right. So if I put a 2 here, not only does that balance my lithiums, that also gives me 2 oxygens, plus the 2 oxygens here is 4, and on this side of the equation, there's 4 oxygens. And this gives me 2 hydrogens, and on this side, there's 2 hydrogens. So this actually balances the equation just by adding that coefficient of 2. So now it's balanced, right? Sweet. Okay, and again, I know that nothing is written Nothing's written here or here or here, but that's the same as coefficients of 1. So once we balance the equation, we're going to convert the grams of the substance given into moles. Okay, and we do that by dividing by its molar mass. So we are given 225 grams of CO2. We have to turn that into moles. All right, now to do a conversion, you multiply what's given, something over times something over something else. What you want to find goes on top. We want to find moles, and what's given, grams, goes on bottom. So we're wondering, 1 mole of CO2 is how many grams? That is, what's the molar mass? What's the mass of 1 mole? And to do that, we're just going to look on the periodic table. If we look on the periodic table, carbon is 12.01 grams per mole, and oxygen is 16 grams per mole. And we have 2 oxygens, so 16 times 2 is 32, plus 12.01 is 44.01. So 1 mole of carbon dioxide weighs about 44 grams. If we take how many grams we have and we divide it by the molar mass, grams will cancel, and you'll be left with how many moles of CO2 you have. So I'll jot this down, but I'm going to leave it on my calculator and just round at the end. So 225 divided by 44.01. I'm going to leave this number in my calculator. Okay, I'll just jot down here for the sake of writing 5.11 moles. Okay, so we just converted from grams to moles. Now, we're actually right back to where we were before with our mole-to-mole stoichiometry problem, right? Because now we actually have moles of something, and we're going to go to moles of something else. This middle part is just like we did before. I'm going to take what's given. So I have 5.11 moles of CO2, and I'm trying to find out something about LiOH. That's what they were asking me about. The question asked how many grams of LiOH are needed to produce 225 grams of CO2. So what I'm given goes on bottom, CO2. This is just a mole-to-mole conversion, right? We're going from moles of what's given. Okay, I know we turned it from grams into moles, but now we're going from moles of what's given to moles of what we're trying to find. Okay, moles of what we're trying to find. Now, based on the balanced equation, the coefficient in front of LiOH is 2. So in front of this we put a 2, and in front of CO2 we put a 1. That's our mole ratio, 2 over 1. Now, I still have this left in my calculator, so I'm just going to say times 2. And again, I'll jot this down, 10.22. Now, moles of CO2 cancels out, and this is now moles of LiOH. So this middle part was just a mole-to-mole stoichiometry problem. But before we could do it, we had to turn grams into moles. Now, you could probably imagine this is called a mass-to-mass stoichiometry problem, meaning we're going from grams to grams of something else. We went from grams to moles, and then we went from moles of what we're given to moles of what we're trying to find. The final step is to convert from moles of what we're trying to find into grams of what we're trying to find. So we need to convert 10.22 moles of LiOH into grams of LiOH. Again, anytime we're converting, we say times something over something else. What we're trying to find goes on top, grams, and what we're given, moles, goes on bottom. 1 mole of LiOH is some number of grams. Again, what's the molar mass? So Li is 6.94, O is 16, and H is 1.01. So we're going to be adding those here. I'll add those together. So 1.01 plus 16 plus 6.94. So our molar mass is 23.95 grams for 1 mole. So that's how much 1 mole is. Okay. and I'm going to be multiplying it by how many moles we have, which is 10.2249-ish. So I did a little bit of rounding, but how that's going to work out is moles of Li will cancel, and we have 245 grams of LiOH needed. And this is our final answer. Okay, so just kind of zooming out a little bit, or looking at where we started and where we are now. There are three basic steps, right? This is what we started with. We started with 225 grams of CO2, and we ended with 245 grams of lithium hydroxide. Now, what that's saying is, to completely react all this CO2, this is how much lithium hydroxide is needed. We couldn't figure that out just based on the mole ratios in the balanced equation. We had to convert grams into moles, and we did that by dividing by the molar mass of what's given. We then did a mole-to-mole stoichiometry problem, going from moles of what's given to moles of what we're trying to find, and we used the mole ratios from the balanced equation. And then we converted from moles of what we're trying to find into grams of what we're trying to find by, in this case, multiplying by the molar mass. This is the basic mass-to-mass stoichiometry process. Now, I broke this down into 3 steps, but it's pretty common to have them written out just sort of on one line. So I'll do at least one example of that when we're doing practice problems here. Okay. So, question, we have 3 practice problems which we'll go through, and hopefully by the end of watching this, you'll be just kind of like, yeah, I got it. So it says, I don't know why that A's there. It says, how many grams of silver are produced when 36.92 grams of copper displaces silver? So this is the reaction, copper displacing silver. What's happening is the copper and the silver are going to switch places. It's called a single displacement reaction. And so then copper is going to be paired up with the NO3, which we have over here, and silver is by itself. So first of all, we need to make sure, we have to see, is this equation balanced? Okay, looking at this, I have 2 nitrates here. You can see NO3 is with the parentheses 2. So that's not balanced. So I have to put a 2 in front of this. And if I put a 2 in front of that, that gives me 2 silvers, so I have to put a 2 here. Okay. So now the equation's balanced. 1 copper, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. So it's balanced. Okay, sweet. Now we're actually ready to begin. So first, we take what's given, okay, which is 36.92 grams of Cu, and we have to turn that into moles. 1 mole of Cu is some number of grams. Okay, now if we look on the periodic table, copper has a molar mass of 63.55 grams. All right, and if we do this, grams cancels, and we're left with moles of Cu. So I'll put this in my calculator. 36.92 divided by 63.55. Now I'm going to leave this in my calculator. Okay, I'm going to just jot down 0.581. I'll just jot that down, but I'm going to leave the number in my calculator and round at the end. So we converted from grams to moles. Now we're going to take our moles, 0.581. This is moles of Cu, and we're going to convert it into moles of what we're trying to find, which they're asking about silver. So Ag, which is silver, goes on top, and Cu, which is what we're given, goes on bottom. These are moles. Okay, we're now going to use the mole ratios from the balanced chemical equation. In front of Ag, we have a 2. In front of Cu, nothing's there, so we have a 1. So just still with this number in my calculator, I'm going to times it by 2. And that gives me 1.16 moles of Ag. So I took grams of what's given, I converted it to moles by dividing by the molar mass of Cu. This just comes from the periodic table. And then I took moles of Cu and converted it into moles of silver using the coefficients from the balanced equation. Now it's not asking how many moles of silver, it's asking how many grams of silver. So the last step is to take our number of moles of silver and convert it into grams. So if I'm trying to find grams, that goes on top, and mole goes on bottom. Now, 1 mole of silver weighs some number of grams. That is, what's the molar mass of silver? So if you look on the periodic table, silver is 107.87 grams per mole. So each mole weighs that much. And we have a little over 1 mole, so we're going to have 100-something grams. Now, I'm just still have this number in my calculator times 107.87. We get about 125. Okay, and moles cancel, that's 125 grams of Ag. Right? This is mass-to-mass stoichiometry. You're given grams of something, we're going to grams of something else. You take grams and you divide it by the molar mass to get moles. You then do a mole-to-mole stoichiometry problem using the balanced equation. And then you convert moles of what you're trying to find into grams. Right? So the first step is dividing by the molar mass of what's given. And then at the end, you're actually multiplying by the molar mass of what you're trying to find. Now, I have written this out 1 line, 2 lines, 3 lines. Okay? I'm going to do the next problem in kind of like a more typical way where it's not written out quite as much. But you can see this is like just writing them in a line is actually how it's more typically done. So this question says that you have a certain number of grams of iron reacting with water. How many grams of iron 3 oxide are produced? So first, of course, before you do anything, we have to balance this equation. This has 2 irons, and we only have 1 iron on this side. So it might be tempting to put a 2 here, right? But if you put a 2 here, the irons would be balanced, but your oxygens wouldn't. And we would have to put, let's say, a 3 here, which I guess this would work, right? If we put a 2, and then we put a 3, that's 6, so we put a 3. Okay. So that's 2 irons on both sides, 6 hydrogens, 3 oxygens, 3 oxygens. Okay, so that's our balanced equation. So instead of writing them out in 3 separate lines, I'm just going to do the steps in one string. So I'm going to write 42.84 grams of Fe times something over something else, right? 1 mole Fe is some number of grams. And if we look on the periodic table, iron has a molar mass of 55.85 grams per mole. So this first step is converting from grams to moles. Now, I'll do this, and I'll just leave it on my calculator, okay? So 42.84 divided by 55.85. This is now moles of iron, okay? But I'm not even going to write it out. I'm just going to go on to the next step, okay? The next step is converting from moles of iron to moles of Fe2O3. That's it. Fe2O3. Sorry if that's hard to read. And on the bottom we have moles of iron. This is the mole ratio from the balanced equation. In front of Fe2O3 we have nothing, we have a 1, and in front of Fe we have a 2. So on here that's the same, times 1 divided by 2 is the same as divided by 2, it's 1/2. So I'm just doing this in my calculator and leaving it there as I go. This number is now moles of Fe2O3. Right? So we took grams of Fe and divided by its molar mass to get moles of Fe. We then multiplied by the mole ratio, and that gives us Fe2O3. I'm just rewriting this because it was messy. Sorry about that. And now our final step is to convert from moles of Fe2O3 to grams of Fe2O3. 1 mole of Fe2O3 is some number of grams. So the molar mass of that, we will have to add that up. So 55.85 times 2 is some number, plus oxygen is 16, so I'll type this out. 16 times 3 is 48, right? So we're going to add that, and we get 159.7. That's 159.7 grams per mole. If we do this, we'll end up with our answer, and our answer will be in grams of Fe2O3. Okay, so just to show you the string of calculations here, you do 42.84, that's our grams of iron, divided by 55.85. That is this first step, which is moles of Fe. We're now going to convert to moles of Fe2O3, right, divided by 2. That is now moles of Fe2O3, and then we're going to multiply by the molar mass of Fe2O3, which is 159.7. And this number that we get out here, 61.2, is now grams of Fe2O3. Right? So these are the same 3 steps that we did in a problem like this, right? Step 1, step 2, step 3, and I just wrote out what they were each time. But most of the time people do stoichiometry, they just do a string like this. And if you look at this, grams of Fe cancels, then moles of Fe cancels, and then moles of Fe2O3 cancels, and you're left with grams of Fe2O3. All right, all your units cancel out along the way. So we'll do a final problem, and then we'll be done. So you begin with 16 grams of ammonia. How many grams of water is H2O, will be produced? So we're going to do this one a little bit quicker. 16 grams of NH3 times something over something else. 1 mole of NH3 is 17.04 grams. So that's just the molar mass. If we take nitrogen, which is 14.01, and 3 hydrogens, hydrogen's 1.01, so 3 of them is 3.03 plus 14.01. This is our molar mass, okay? And then our mole ratio, this equation's already balanced for us, which is really nice. What we're trying to find is water, so H2O goes on top, and what we're given is ammonia, so NH3 goes on bottom. These are moles, and based on the balanced equation, in front of water we have a 6, and in front of ammonia we have a 4. So this first step, dividing by the molar mass, will convert from grams of NH3 to moles of NH3. We then multiply by our mole ratio, which is based on the coefficients from the balanced equation. This will give us moles of H2O. And then we're going to convert from moles of H2O to grams of H2O. And we're going to do that by multiplying by the molar mass of H2O. Okay? Oxygen 16, hydrogen's 1.01. So 2.02 plus 16 is 18.02. That's the molar mass of water. If we do this, we end up with grams of H2O. So I'm just going to do this all in one calculation here on my calculator. 16 divided by 17.04 gives us, that's now moles of NH3, times 6 divided by 4. This is now moles of water times 18.02. This is now 25.4 grams of water. and that is our final answer. Step 1, convert from grams of what's given to moles of what's given by dividing by the molar mass. Step 2, do a mole-to-mole conversion by putting the moles of what you're trying to find on top and moles of what you're given on bottom using the balanced equation. And step 3, convert moles of what you're trying to find into grams of what you're trying to find by multiplying by the molar mass. So step 1, you're dividing by the molar mass of what's given, and then in step 3, you're multiplying by the molar mass of what you're trying to find. Units cancel out all along the way. Grams NH3, grams NH3. Moles NH3, moles NH3. Moles H2, moles H2. All you're left with is grams of H2. This has been a video about both mole-to-mole and mass-to-mass stoichiometry. Hopefully after watching this you feel a little bit more confident about your stoichiometry skills. Hopefully you enjoyed that. I had a lot of fun with it. I was stoiced to do this video. See what I did there? Enjoy.